Hi, my name is Heather, and I did my topic on undersea cable technology. In today's world, we are constantly connected to people from all over the world. We can send, receive messages almost instantly, and can stream movies from practically anywhere. This is due in a large part to undersea fiber optic cables. Not many people know this, but 98% of our international internet traffic is ferried around the world by undersea cables. Despite this, many people barely even know that these cables exist. So we're going to discuss what is undersea cable technology, the history of it, why it was invented, how it's implemented, how it works, and the laws regarding it. So what exactly are undersea cables? As the name suggests, it's basically long wires that are laid on seabeds to carry telecommunication signals. It also is sometimes referred to as submarine cables. It's impressive to think about and something that not many people are aware of going on under the sea. Anytime that we make a phone call to a friend overseas, send out an email, download or upload a video on YouTube, we are transferring data. Whenever we transfer that data, it needs some sort of medium to carry from source to source. This allows the world to stay connected and carry the data to different locations. This picture to the right is kind of an example of what's going on under the sea, and if you were to splice that cable, what it may look like. Right here is a map of all the cables that are currently around the world. If you go to that website, you can interact with these cables and get more information about them. Our story begins with the telegraph first being developed by Samuel F.B. Morse. While he wasn't the first to propose the idea, he was the first to get a working telegraph instrument by the 1830s. It's in the late 1830s that he perfected the Morse code, and then in May 1844, the first message was sent from the U.S. Capitol to a railroad station in Baltimore. It was then in 1854 that Cyrus Westfield conceived the idea of the telegraph cable and secured a charter to lay a well-insulated line across the floor of the Atlantic Ocean. It took another 3 years before that line started to be laid, and another year before they were actually successful at laying the cable. There were many failed attempts, and they had to keep starting over, especially when they didn't have a way of communicating with one another at the time. It was then on August 16, 1858, that the first exchange between Queen Victoria and the current President James Buchanan, was able to take place. It connected British North America to Ireland. However, it wasn't nearly as instant as what we are used to today. It took nearly 16 hours to send the full message through the 3,200-kilometer cable. It was still quicker, however, than the normal means of communicating messages across the seas at that time. It normally would take months to be able to send a message across the seas. The cable didn't last long, though. It had deteriorated within the month. However, it did give hope and promise to the future of what communication could look like. In the initial stages of creating this cable, there was a lot of debate surrounding how the cable should be created and how it will hold up against the elements. Some believe the submarine cable should be as narrow as possible to limit retardation of the signal, and with a wider cable that meant more electricity would be needed to charge it. The other side argued that the amount of retardation was inversely proportional to the square of the cable's length. Using a large diameter core made with the purest copper available to reduce the resistance. The latter didn't happen though due to cost. Over the ensuing years since the first transmission, techniques improved with the addition of inline amplifiers or repeaters to allow that signal to be propagated across longer distances, and progressive improvements in signal processing to improve the capacity of these systems. Eventually, telegraph turned to telephony, valves turned into transmitters, and polymers replaced rubber, but the basic design remained the same: a copper conductor sheathed in a watertight insulating cover with steel jacketing to protect the cable and the shallower landing segments. The cables that are in the ocean today are about the size of a garden hose and can last up to 25 years, if not longer. Off to the right, you can kind of see what the first cable looked like that was laid in the ocean. This was something that they sold at the time as a souvenir, but after it failed, it became more of a relic to have, and there is a piece in one of the museums. So what happens when the cable fails? Generally, the public isn't going to notice. There are protocols in place to repair the damaged line. If it isn't repairable, then the cable may be left to just sit at the bottom of the ocean. However, there are companies who will obtain the rights to pull the cable up and salvage the raw materials. Many companies will spread their network over numerous cables so a user will not notice a breakage in the lines. There was a concern in 2008 when North Africa and Persian Gulf all suddenly went offline or the internet speeds had slowed considerable. 3 damaged cables were located, but only one of them could be explained as to what caused its damage, and the other 2 were speculated to be cut maliciously. Some causes for cables failing include accidental and natural damage, such as fishing vessels, dredging, anchor dragging, and extreme seismic and weather events. Malicious damage includes cyber attacks, state and non-state actor sabotage, cable cutting, vandalism, and theft. So are these fiber optics cables secure? Earlier I discussed how it speculated that the cables had been cut. This is still a major concern today, as many of the lines are just sitting on top of the seabed and don't have much protection. If someone really wanted to sabotage the global internet, it would have to be done simultaneously on multiple cables. Most of the attention on maritime security vulnerability is devoted to the transportation system, which includes vessels and ports. Often neglected aspect of the domain concerns the vulnerability of arguably the most important critical infrastructure. Another concern with these cables is them being tapped and information gathered that is transported over the lines. While it's extremely difficult to do, it's not impossible. Attackers can also knock out parts of a network that they can't surveil and force people onto cables that they do already control. The target then would not even realize that their communication is being exposed. So, what are the laws regarding these undersea cables? Understanding the international laws governing cables is essential to protecting them. International law differentiates between attacks on cables and espionage. The earliest international law agreement is the Convention on the Protection of Submarine Cables, which was signed in Paris in 1884. The treaty applies to all cables outside the territorial waters of states and requires all states to incorporate its protections into their domestic law. Article 2 mandates that the breaking or injury of submarine cables done willfully or through culpable negligence shall be a punishable offense. In Article 12, the parties agreed to implement national legislation to impose the penalties for violating the treaty. Notably, Article 15 says its provisions shall in no wise affect the liberty of action of belligerents. Thus, in wartime, the protections do not apply. Maritime law is also important to undersea cable governance. The 1958 Geneva Conference on the Law of the Sea addressed submarine cables in 2 treaties, the Convention on the High Seas and the Convention on the Continental Shelf. Article 27 addresses damage to cables, but it does not explicitly prohibit the intentional damage to them. Instead, it mandates that states party to the treaty take the necessary legislative measures to make breaking a cable a punishable offense. Again, in 1982, the UN Convention on the Law of the Sea superseded the 1958 Geneva Conventions. This landmark agreement addressed submarine cables in multiple chapters. It established exclusive economic zones, also known as EEZs, waters 200 nautical miles beyond states' territorial waters in which they enjoyed sovereign rights to undertake economic activities. Among those activities, the law recognizes the freedom of all states to lay cables within the EEZ and extended its protections to cables within the EEZ. As of current, there are no existing treaty addressing cyber warfare operations. While existing treaties do offer some legal protections for cables, a camp of international lawyers contends that cables become legitimate objects of attack in wartime. In practice, the lack of legal disputes involving attacks on cables leaves their legality uncertain. So how is it implemented? We've discussed a little about what undersea cable technology is, what it's made of, how it works, but let's get into how they even implement it. The FCC, also known as Federal Communications Commission, and various agencies are involved in the oversight of the submarine cables and/or other undersea activities that may impact submarine cable infrastructure. The FCC International Bureau grants licenses authorizing cable landing, license applicants to own and operate submarine cables and associated landing stations in the United States. There is a growing number of private companies that are building their own networks of fiber optics and then can lease them out to the highest bidder. Google just recently announced their plans to build a new undersea cable with landing points in New York, the UK, and Spain. Some other corporations joining Google include Facebook, Microsoft, and Amazon. They do actually own a good chunk of the cables that are active right now. The actual laying of the cables is a years-long process and can cost upwards of millions of dollars. The process starts with looking at naval charts to plot the best route. They are the safest in deep water and away from things it could rub against like rocks or other disturbances. The biggest concern is when you get closer to shore where it can be disturbed easier. In some spots, it may be necessary to build concrete trenches to tuck the cable into for protection. This may be closer to land where people can tamper with the cable. Some areas they try to avoid include areas with lots of undersea currents, volcanic areas, and avoiding lots of elevation change on the seafloor. Once the route has been plotted, special cable laying ships begin putting out the cable. It can take a month or more just to get the cable on the ship. These cables aren't light either. 4,000 miles of cable can weigh over 10.2 million pounds. So how do they work? As of early 2021, there are about 426 submarine cables in service around the world. This number is constantly changing due to new cables being introduced and older cables decommissioned. There are lasers on one end that fire at extremely rapid rates down thin glass fibers to receptors at the other end of the cable. These glass fibers are wrapped in layers of plastic or steel for their protection. It offers a high capacity of up to 2 Tbps per cable, but this is going to vary depending on how old they are. They also have a real-time transmission with very low bit error rates. So could these cables ever be replaced in the future? Undersea cables have dominated the network industry for over 150 years, so I'm not sure if they're going to be easily replaced. However, it is speculated that satellites could be the next big thing. Elon Musk has revealed his plan to surround the world with low Earth orbit satellites called Starlink. This is going to bring satellite broadband internet service to the world. The FCC has already authorized SpaceX to fly 12,000 satellites and could go upwards to 30,000. So it would seem that the FCC is on board with rebuilding the internet in space. The downside to satellites is they may only offer 1,000 megabytes per second, and they do display a high latency. Another downside is cost. Undersea cable technology, despite costing millions on its own, is less expensive than implementing satellites. As of right now, undersea cables and satellite are our only means of transporting data. So what does the future hold with these undersea cables? For the internet to thrive into the future, speed and capacity are critical. The coming population boom and the subsequent demand for more information and the ability to get faster speed requires a pretty fast internet with high bandwidth. In other words, the ability to carry more data at faster speeds. The IDC predicts that the global datasphere will grow from 33 zettabytes, which was in 2018, to 175 zettabytes by 2025. To put that into perspective, consider that if each terabyte and a zettabyte were a kilometer, it would be equivalent to 1,300 round trips to the moon and back. Or, as former Google CEO Eric Schmidt puts it, from the very beginning of humanity to the year 2003, an estimated 5 exabytes of information was created, which corresponds to only 0.5% of a zettabyte. While satellites are still being looked into as a viable option to transport data, undersea cable technology will probably keep expanding and growing to keep up with the demand. Many companies are still pumping millions of dollars each year into growing the undersea cables. In conclusion, the undersea cables aren't going anywhere anytime soon. They're critical to helping propel forward our internet access, ensuring that all parts of the world are able to get it. I'm sure satellites in the future may help with some of this load, but only time will tell if they completely change the way we access the internet.